Hi, I'm Lene, and the topic I'm going to be discussing today is optical character recognition for Braille documents, or OCR. And this might sound a bit strange at first, but just bear with me, I promise it'll make sense. So, first of all, OCR is a technology that allows computers to read or recognize text from images or scanned documents. However, in this case, the text we are trying to detect is Braille. Now, Braille is a communication system for people who are visually impaired, and it uses patterns of raised dots that can be felt, and each combination of dots represents either a specific letter or number or punctuation mark, or sometimes even phrases. And you can see some examples of scanned Braille documents on the screen to the left. So at the top, we have a complete Braille document that's been scanned. At the bottom, I've blown up some of the little character groupings so you can see them a bit more up close. And a single Braille character can have at most 6 dots, and you can see some examples at the bottom. So why would we want to do OCR on Braille documents? So as you know, almost everything is digitized these days or can be digitized. We can use our phones to take pictures of pages containing text, or we can feed those pages into a type of scanner and extract the text from those physical pages in a digital format. And many educational institutions or libraries actually have an interest in doing the same for Braille documents, since they want to either preserve the content of those documents. As you can imagine, many people over many years touching the same little dots, it causes some messes, or they just want to extract the text so that sighted people can actually learn Braille. And as you can imagine, text detection can be a bit difficult when the page doesn't actually contain any ink or clearly visible markings. So the only way we can detect Braille is by detecting and interpreting their shadows. A machine learning approach would have made the recognition process much faster and much easier, but me being me, I of course had to take the tedious route and explain manual digital image processing approach instead. So let's hop into the general process. Now, in a perfect world where we could hypothetically see each Braille dot as a perfect visible circle on an image, as you can see in the top left, we would have to follow the following steps. First, we want to put the image through a process of pre-processing, which includes converting the image to grayscale and then to a binary image. Now, a binary image contains only black and white pixels. Next, we can detect the contours on the image, and this will help us locate markings, thus the dot shadows on the page. Next, we can find the midpoints of these contour blobs and use them to construct a grid. Now, this grid will be used to realign the dots that aren't on the same X and Y axes, and also determine where the characters are supposed to start and end. Next, we can isolate each character on the page and map it to a numeric array, and then use that numeric representation of the character to determine what type of character it actually is. So it's almost like an ASCII conversion where you have the numeric value representing a certain symbol. It's just with Braille. Now, in a realistic world, this process becomes a bit more convoluted since actual scanned documents contain many imperfections and a lot of noise due to either scanner resolutions or just marking on the pages from people touching them or messing stuff on them. So here we have the actual process. In image 1, we have the scanned documents, and as you can see, there are many noisy shadows on this page. Now, our aim is to try and remove as much of this noise as possible. And to do so, after converting the image to grayscale, we first blur the image, and this will soften up the noise a bit. Next, we convert this image to a binary image where we can see the noise a lot clearer. And then we can apply morphological erosion to the image. Now, this will filter out any small disconnected pixel groups, since they are most likely related to noise and not the region of interest. Then we can apply morphological closing, and this will fatten up the remaining parts so that we can get a more rounded blob instead of this awkward shaped little thing. Then we can detect contours, find the midpoints, and use these midpoints to construct a relative grid based on the measurements between the dots. We can then realign the dots so that those belonging to the same rows and columns are actually on the same X and Y axis lines. And finally, we can isolate and interpret the characters individually and translate the whole page from Braille to normal text. Now, I'll just be showing you guys a couple of the pre-processing steps a bit more up close so you can see why they're actually important and necessary. So here we can see the binary image. And if you look at the top, there's a little dot that's been isolated, and there's a lot of noise around this dot. Now, when we apply morphological erosion, we're essentially eroding away most of this noise, at least. And you can see the effects of erosion on the right. But sometimes erosion can cause this dot to actually become segmented into two sections. And why we don't want that is because when we determine the midpoints of these blobs, where we want a single midpoint, this will give us two midpoints, which could result in inaccuracies when translating from Braille to text. So when we apply morphological closing, we're puffing up this little dot a bit to give us a bigger blob, and it'll give us a more accurate midpoint of where this dot actually resides on the image. Here you can see the contours that we've detected and the midpoints relating to them. Now, on the midpoint image, where all of the blobs have been reduced to a single pixel, essentially, you can see that even though some of them were meant to be in the same row and column, they're not perfectly aligned. The reason why we want to align them perfectly is so that we can more accurately determine where the character is supposed to start and end, and where the next character is supposed to start and end, so that we don't accidentally extract the wrong character or certain dots from the next character, put them into the first character's thing. So here you can see an image of where the dots have all been realigned in their grid, and they can then nicely be extracted and translated. So the translation process is as follows. On the far left, you can see we have a single Braille character that comes from a scan. So after putting that character through the entire process, we end up with this binary image containing only little white pixels, which represent our dots. Now, since a Braille character can only have at max 6 dots, we can analyze this image and see, okay, in which sections of this image are there little white dots? And then we map that to a binary array. So if there is a dot present in a certain section of the image, we put a 1 in the binary array. If not, we put a 0. Then we take this binary array and we map that to the following numeric array, where we can build up a number for this character. So if there is a 1, we take a 1. If there's a 1 in the second position, we take a 4, etc., etc. So this Braille character's numeric representation is the number 145. We can then do a dictionary lookup to determine what letter or character that represents, and we come up with the letter D. So we repeat this process for every single character that we've detected on the Braille scan on the page, until we have finally and successfully translated the whole Braille document to text. So yeah, that is the process of OCR for Braille documents.